Okay, before we start this lesson, it is a good idea to download the Word document, which is also attached to this week's work, which is a summary table for component characteristics, and it has 5 different components, and it asks you to record information in a table. That summary table covers everything in this lesson, so you will be required to pause the video at different points and fill in your table. Once you've got the table in front of you, either printed out or written down, I'd like you to start off by answering these questions based on the 2 experiments that we've looked at in previous weeks. So number 1, how do we measure current? Number 2, how do we measure voltage? How do we connect voltmeters and ammeters? Which 2 components did I show you an investigation of? And please describe both of your graphs in a paragraph. There is an extension question if you get on to that. So you should have had a chance to do that now. And these are the answers that you could have come up with. So number 1, how do we measure current? Well, we measure current with an ammeter. And if you're drawing its circuit symbol, it would be a circle with an A in it. Number 2, how do we measure voltage? Well, we measure voltage using a component which is called a voltmeter. Number 3, how do we connect voltmeters and ammeters in electrical circuits? Well, we always connect ammeters in series with the components that we're testing, and voltmeters must be placed in parallel across the components. Now that is because voltmeters have an infinite resistance to accurately measure potential difference. So if you put them in a series circuit, they just stop the flow of current completely. Number 4, which 2 components did we investigate? Well, we investigated fixed resistors and filament lamps. So number 5 is a little bit more tricky, and it says to describe both of your graphs in a paragraph. Now I've got what I would define as the perfect explanations in the following slide. And these are what our 2 graphs look like. The top one was for the fixed resistor, the bottom one was for the filament lamp. And as we've already looked at, the fixed resistor has a constant gradient because the resistance of it never changes, so it has a linear relationship. And if we were to explain that in a paragraph, we might write something like, components which show a straight line are often named linear circuit elements. They're also sometimes called ohmic conductors. This means that basically the current is directly proportional to the potential difference for that component. So as the voltage increases, the current increases by the same amount. And this is called Ohm's law. So this component is obeying Ohm's law perfectly. It's true for fixed resistors or resistor wires, but it is important that the temperature stays constant, because if the component gets hot, then it will not produce a linear graph as shown. Now, as we saw with the filament lamp, it was non-linear. It was more of like a flattened out S. And the first bit was almost a copy of Ohm's law. So for the first lower voltages, the current does increase in line. But as filament lamps become hot and glow, the shape of the graph changes as the temperature of the component changes. So when the component becomes hotter, when you increase the voltage, the atoms in the metal of the wire, they vibrate more. And that means that the electrons which are flowing through it collide more with the atoms which are vibrating because of the extra heat. And this increases the overall resistance of the component, and an increase of the potential difference will only make the atoms vibrate more. So less current can flow through. So the graph shape sort of tapers off a little bit, and the current doesn't increase in line with the voltage, which results in the shape of graph as we've seen on the left. So today what we're looking at is a summary of the 3 components we've looked at, and we're going to look at 2 additional components and look at the graphs associated with them. So we're going to look at an investigation with resistors, filament lamps and diodes, and evaluate which ones are ohmic conductors. We're going to explain the shape of graphs, which we have already, and then we're going to move on to describe the properties of thermistors and LDRs. Now, it's a good point now to pause and make sure that you have copies in your notes of the 3 graphs, okay? So the first one is the fixed resistor, the middle one is the filament lamp, and the one on the far right is for the diode, which again only conducts in one direction. And then again, it would be really good if you could consider the question that it says here. What key phrase do you use to describe the graph if it follows Ohm's law? So if something is following Ohm's law, we could say that it's increasing in a directly proportional relationship. So the current increases in line with the voltage that applied across it, so you get a constant gradient. You might have a range of different gradients, but the key aspect is that the gradient never changes. So if you plot it on a graph, you get a linear relationship. Now you do have to be able to draw from memory the 3 test circuits, and we've seen this test circuit before. We've got the component that we test in series with an ammeter and a variable resistor. And the variable resistor allows you to change the voltage that's applied across the component. And in parallel across the component that we're testing, we have a voltmeter. So pause the video now and see if you can draw from memory the 3 different circuits which would be identical apart from you change the symbol for the component that you're testing. So the first one that we need to look at is a fixed resistor. So your circuit would look like this. Your second circuit would have a filament lamp. So you would just insert the filament lamp symbol there. And if you wanted to create your third one, you just swap in the circuit symbol for a diode. Now remember, we've seen before that diodes can only conduct in one direction, which we call the forward bias. And the direction that you connect them in is shown by the direction of the arrow on the circuit diagram. So you can see that this arrow is pointing towards the right hand side, which means that this component would only conduct if you connected it with the current flowing in that direction. If you reverse the current, okay, you would get the negative set of readings on the graph, which are very, very close to 0 on the axis. Okay. Now, once you've got those, just pause the video and go through and make sure you've filled in your table, because there's 3 graphs. You need to record them in your table with the circuit diagrams and the summaries of what the graphs show. And when you've finished, let's go back and look at these 2 new components. So these show not current voltage graphs, but they show resistance temperature graphs and resistance light intensity graphs for 2 components. One is a thermistor and one is a light dependent resistor. Now the circuit symbols are shown on the slide along with the graphs. Now you need to put that information in your summary table that you're filling in throughout this lesson. And you also, on a separate piece of paper, need to answer questions 2 and 3 for the thermistor and 2 or 3 for the light dependent resistor. So pause now, complete that, and then I'll go through the answers with you. So, describing the pattern of a thermistor. Well, as the temperature increases, the resistance drops. And you can see that it's kind of a curved relationship. So the resistance drops quite dramatically for low temperatures, but then the rate decreases, so the curve flattens out. We can also say that this is a non-linear relationship because it doesn't decrease in a straight line. Can you think of any uses for thermistors? Well, if you do resistant materials, you may come across thermistors in any temperature sensitive circuit. So a circuit that's required to adjust its functionality with the temperature, for example, in a fridge. Light dependent resistor, it's got a similar relationship, but obviously we're talking about different quantities. So in this case, we're talking about the light leveling. As the light level increases, the resistance drops. Again, it's a non-linear relationship. So the first bit of the curve is quite a dramatic decrease, but then as the rate decreases, as the light intensity is still increasing, the rate of decrease drops, which again leads to the curve flattening out at the bottom. It's a non-linear relationship in the same way. And this is used in sort of light sensitive circuits. So an alarm clock, for example, that would come on, okay, as the daylight increases. So pause now, add this information to your table, and then we'll move on. Now in this section, we're going to go through some summary exam questions just to double check that you've got a really good understanding of what we've looked at. So your table now should be full, and you can use the table in front of you to answer these questions. If any part of this doesn't make sense, you probably need to go back and have another listen to the various slides just to refresh in your memory what we've looked at. So, question 1. Complete the sentence. Choose answers from the box to go in the blank spaces. So pause now, write it out, and pick the appropriate answers which fill in the blank spaces. So the current through an ohmic conductor is directly proportional to the potential difference across the component. So current is increasing in line with voltage, provided that the temperature remains constant. Remember that if a component gets hot, its resistance will increase dramatically, and it won't be a straight line graph. It'll be more like the graph for a filament lamp. Question 2. Figure 1 shows a current potential difference graph for a filament lamp. Explain how the resistance of a filament lamp changes as the potential difference across it increases. So again, pause now, write out the question and write out your response. Now this is a 2-mark question, so you'll have to provide a fact, and then you'll also have to justify your answer with some scientific information. So we can see that the current increases as the potential difference increases, but that then causes the temperature of the filament in the bulb to increase, which again means that the resistance increases. So therefore, if resistance increases, the rate of increase of current must drop off because it's harder for the electrons to be flowing through the circuit. Final question. Now this is looking at a light-dependent resistor, and on the right-hand side I've included the graph just to remind you of the relationship of a light-dependent resistor. So again, as light intensity increases for a light-dependent resistor, the resistance of it drops off. So the light intensity decreases, not increases, but decreases. What happens to the potential difference across the light-dependent resistor and the current in the LDR? Well, the first thing is that the potential difference would increase because the current has decreased. Now the current has decreased because as light intensity drops, resistance of an LDR increases because it's harder for the electrons to flow through the component at low light levels. Now, if resistance across a component is higher, that means more voltage will be recorded across the component. So therefore, the resistance increases. Now that relationship is just something you need to be aware of, that the higher the resistance across a component, the higher the potential difference will be across it as well. Now we've covered quite a lot in this, and it is really important that you've got a full table summarising all the information, and also that you can understand how to answer any of these questions. If none of it makes sense, you can drop me a comment on Show My Homework. But what I would advise you to do first is to go back and watch it again, because a lot of this is really technical, but once you've run through it a couple of times, it does make sense, I promise.